Good morning. Today's lesson we're going to learn about perpendicular, parallel, vertical and horizontal lines and something called an axiom. We're going to start off with perpendicular. It's quite a difficult word to pronounce. Can you have a go? Perpendicular. Well, if something is perpendicular, then it has created a right angle. And if you remember, a right angle is 90 degrees, like the corner of your book. So if we have two lines that are perpendicular, it means that they are at right angles to each other, like this. So here you can see we have line M, and we know it's a line because we've got the small lowercase m. And then we've got a line K. And they are intersecting at this point of intersection. Remember that intersection means they're crossing. And the measurement of these four angles then that they've created between them are each 90 degrees. Exactly parallel and vertical and horizontal. If you were to turn slightly to the side. So it's like four corners of a page will fit perfectly into this. And 90 plus 90, another 90 and 90 makes 360 degrees, which makes sense. We know that that's the full rotation of a circle, and altogether all four of those will create 360 degrees, a full circle. So these two lines, line M and K, are perpendicular. Now, like with a lot of maths, we like to use symbols to label or notate what we see. So instead of writing M is perpendicular to K, then we can use this little symbol here. It's like an upside down T, a very small one, but it itself is a pair of perpendicular line segments. The two have 90 degrees between them. So this is how we would write K is perpendicular to M. The lowercase k for the first line, the symbol for perpendicular, and then our second line, M. Next, let's look at parallel lines. Parallel lines always have the same distance between them, and that means that they will never ever intersect each other. It doesn't matter where you measure, somewhere closer to minus infinity, somewhere close to zero, somewhere close to positive infinity, but they will always have the same distance between them. Let's have a look. So look, we have two lines, P and Q. And if I was to measure across here, it might measure 2 centimeters apart. And if I was to measure here and here, it would also be 2 centimeters apart. In fact, it doesn't matter where I would measure, the distance between the two then will always be the same. So that's what we mean by the two lines being parallel. And if you look onto this diagram, we have got an arrow on both of these lines. And that's how we can show on our drawing, how we can represent, we know that that means to draw in maths, that two lines are parallel by having the same number of arrows on them. So what is the notation for parallel? Just like we had a little symbol for perpendicular, the upside down T, we have a small pair of parallel lines together that are vertical, like this. If you look, there are two little line segments here, and they both are the same distance apart. They're parallel themselves. So rather than writing P is parallel to Q, we can simply use our symbolic notation and put these two little parallel lines in between them. P is parallel to Q. You can find lots of perpendicular and parallel lines all around you. Take a look around your room. Can you see a lot of them? Well, the corner of my computer screen, that makes 90 degrees. That means this top and the side They're both perpendicular to each other. They've created a 90-degree angle, a right angle. If I look at the top of my screen and the bottom of my screen, they're parallel. There's the same measurement between the two of them. I look at my tapestry, parallel and parallel. The side and the top perpendicular. This side and this side are parallel. Spend a couple of moments looking around your room and see if you can identify different perpendicular and parallel lines. So, lines that are parallel to each other have arrows on them to show that they're parallel. So if you see arrows and the same number of arrows, so these both have one arrow each, then they are parallel to each other. We don't need to measure them. We simply know from the use of these arrows. And here we have 3 lines, line P, Q and R. I don't need to measure in between them to decide that they're parallel because they each have one arrow. So having the same number of arrows means that they are all parallel to each other. The distance between R and P is the same all the way along. The distance between R and Q is the same all the way along. The reason why I've said about having the same number of arrows can be demonstrated in this representation here. Notice that we have 2 lines L and M that are evidently parallel. They have the same number of arrows. They have 1 arrow each. But we also have another pair of parallel lines. But it's quite easy to see that L and P are not parallel. If I measure here to here, it might be 5 centimetres, but if I measure here to here, it might be just 1. So we can't use 1 arrow for P and Q to show that they're parallel, as well as L and M having 1 arrow. We would get confused. So instead, we've got 2 arrows on P and Q, so that we can see they both have the same number of arrows. So those 2 are parallel, but they're not parallel with these 2. But L and M having the same number of arrows, that they're parallel with each other. So we can write that using mathematical notation in this way. L is parallel to M. P is parallel to Q. But L and P are not parallel. So look how we can show this. We can put our 2 parallel lines and it's crossed out. So this means is not parallel to. We're going to learn another important keyword in mathematics, and it's an axiom. In some countries, they call this postulates. A postulate or an axiom is simply a statement that we decide we know is correct without having to prove it. So you have learned a lot of axioms already in the time that you have been learning mathematics. And we're going to look at a few of them today. First of all, axiom 1 is called the 2 points axiom. And this is the statement, the sentence, the fact that we decide, yes, this is definitely true. We don't need to actually prove it. There is exactly 1 line, so there can't be 2, 3, 4 or more, that runs through any 2 points. Let's have a look. If I was to draw A and B, 2 points labelled with their capital letters, and ask 5 of you to draw a line through those 2 points, then you would all draw the exact same thing. It would look just like this. And that helps us to understand that axiom 1 is correct. We cannot draw a line that looks different as long as we have made sure our straight edge like our ruler or our set square, is lined up perfectly with A and B, then we're going to have this same drawing through the two of them. So in other words, we can draw only one line through any 2 points, like our A and B. Now, axiom 2 then is called the ruler axiom. And that's looking at the properties which we know are the rules, or what makes something be like it is, of the distance that are created between 2 points. 2 or 3, let's have a look. We're told that the distance between 2 points, and we've got a capital A and a capital B, and we have these 2 lines either side of them. Can you remember what that means? It means the measure of. So if I was to measure between the first point A and the second B, then it has a measurement of distance. We know that first of all that can never be negative. We can't have a distance that's a minus number. So we could never have an answer that the measure of A to B is -3 centimeters, for example. We also know then that the distance between A and B will be the same as if we measured from the other direction, from B to A. In other words, it doesn't matter which order we put the 2 points inside our little lines, they're going to have the same measurement. If we measure from A to B, it will give the same answer as if we measured from B to A. So if A to B is 5 millimeters, then if we turn our ruler the other way round or our page the other way round, it's still going to be 5 millimeters. It's still the same line segment that we're measuring. And then last of all, we have another option, another point, a point that lies somewhere on that line segment. I'm just going to demonstrate it now to make it a little easier to see. So look, here we've got A and B. And we have a point in between them, C. And that point is collinear. Can you remember what collinear means? It means it's lying on the same line as A and B. So if I've drawn my one line that we know we can draw through A and B, that C lies somewhere on that line in between them. Now, if we measure from A all the way to B, so in this instance, that's 10 centimeters with our ruler, then this axiom tells us that the measurement from A to C plus the measurement from that same C to B must both together make 10 centimeters, because the two small line segments together make the larger line segment. So let's have a look at that more clearly. A to C measures 4 and C to B measures 6, and together 4 plus 6 is the same as measuring from A to B, 10. So that helps us to understand this sentence that is part of axiom 2. If point C lies on AB, so we have a line that passes through the point A and B, and we can see that here. It's continuing beyond A and beyond B. So it's not a line segment, it's a line AB. Then the measure of A to B is the same as the measure of A to C plus the measure of C to B. 10 equals 4 plus 6. Let's check this out for ourselves. I've drawn a line segment, A to B. Okay, let's measure that. So if I line up one endpoint exactly with 0, the other endpoint B then is at 12 centimeters. So my line segment AB has the measure of 12 centimeters. So axiom 2 is telling us that if we measure A to C, that measurement plus the measurement from C to B will together, the two of them, add to make 12 centimetres. Let's check that out. So if I measure AC, so I'm lining up my ruler with 0 and A, then I can see that C is at 4 centimetres. So the measure of AC is 4 centimetres. And let's measure between C and B. It's 8 centimetres. Let's check it out. So if we're correct, then the distance between A and B, which we know is 12, will equal the distance between A and C, which we've just calculated is 4, plus the distance between C and B, 8. Well, 4 plus 8 is 12. We've just shown that axiom 2 is correct. Moving on to axiom 3, well, you actually learnt how to do this in our last lesson. Axiom 3 is the protractor axiom, which simply states that we can measure angles with degrees and that the angle will always between 0 and 360 degrees. So let's have a look. We know that a straight angle measures 180 degrees and it looks like this. So if we take one arm of our angle to be BC, a ray, it's ending at B and continuing through C, and the other arm is B through to A, is this ray, then the rotation between the two is 180 degrees. It also shows us that if we have one angle, so let's take the angle BAD. So remember that means we take the path through B to A to D. That's this largest angle here. And that's shown with this big arc, number 3. That this angle, if we suddenly cut it into two smaller angles, so by creating this ray AC, we've now got an angle between CAD, which we could call angle 2, and we now also have an angle BAC, which we can call angle 1. That together, angle 2 and angle 1, they make the same amount of degrees as the entire angle 3. So if an angle is divided into two smaller angles, then those two smaller angles will add to make the original degree. And let's check that we can understand that in notation form. Angle 1, remember the symbol for angle is a small symbol. And these two lines mean the measure of. So the measure of angle 1, this small amount here, if we add that measurement to angle 2's measurement, this one here, so this one plus this one, it will give the same answer as the measurement of the original angle 3. And using correct labelling of angles, like you had to practice in the exercise I gave you last lesson, we can say that using the points that these angles 1, 2 and 3 create if we take the path that they follow. So angle 1 is the same as angle BAC. Here we are. And angle 2 can also be called angle CAD. And angle 3 can also be called BAD. And that's what it would look like if we used that notation of angles. The last axiom that we're going to look at today is axiom 5, and that's the axiom of parallels. And it says that given any line and a point that lies above or below that line, you can only draw one line through that point that will be parallel to the original line. Let's have a look at that in action. We have our line K, and we have a point that's above it in this case. Well, in order to draw a line through that point that's parallel to K, it must have the same distance between it wherever we measure. So that means if I was to ask you all to draw a parallel line parallel to K, but it must pass through this point, then we would all draw this exact same line here. So there's only one possible line that we can draw. We can draw only one line through the point P that is parallel to the line K. One last thing before we go, just for fun. What's Miss Foley's favourite season? Why, it's summer, of course. Summer. Thanks for listening. See you in the next class.